Can you guys hear me well as well as being able to see my screen? All right, thank you, Gavin. Good, thank you. So let's start our lecture today, okay? This is our 8th lecture. If we take a quick look of our Gantt chart, we will see we are at here. We are at here, at this cell, this particular cell, right? A couple of more lectures for this module 3 down the road, and we will have a midterm 1 here. So what are we gonna do on this coming Wednesday? Here, what are we gonna do? Review. Correct. Correct. Okay. We're gonna review. So review what is gonna be covered in the midterm 1, and today we are here. Okay. And today we're gonna do some examples for the symmetrical components, and then on Wednesday we're gonna review. Also talk about the quiz. Okay, and I'm in the middle of grading the quiz 1, and by next Monday, I think I missed some examples for the per unit system. If you recall back to module 2, at the end of the module 2, we didn't have any examples for per unit systems. Am I right? Anyone can recall that? Thank you, Anil. Yeah, Anil remembers. Yep, thank you, Alex. Okay, that's true. So we're gonna have to go through some examples there. I'm planning to do that on this Monday. Closer to the midterm 1, and kind of a more helpful. So this is the plan. Yeah, this is the plan for this module. The rest of the lectures for this module. Any questions so far? Any questions? Any questions regard the, for example, the exam time, the test run exam in the module? Everything went well? Any questions? Any concerns? Anil, can you speak out? It's gonna take forever. All right. Or you can record examples of per unit and post in the Canvas. Well, if I do the recording lecture, obviously it's going to involve those examples in the recorded lectures, so no one gonna miss it, right? So, because we do have time to do that in the lecture. If we don't have time for the examples in the lecture during lecture time, then I will do that. Okay, but I believe we do. I believe we do have time. So I'm gonna talk about it by the lecture. Okay. All right. Coming back to the symmetrical component knowledge. Last lecture we basically learned the all of the concepts about this symmetrical component things. Let's go over them together. Okay, let's go over them together. So first of all, we are using the voltage as the example. However, the current follow the exactly same idea. Okay, so you have 3-phase voltage or 3-phase current, and the in terms of voltage here, we have 3-phase voltage, phase A through phase C. These 3 are called what? Unbalanced 3-phase voltages, right? In your understanding, this means unbalanced means nothing but total, right? Total. What do you mean by total? Because each one of them consists of 3 different sequence components. What does it mean by different sequence component? Phase A unbalanced voltage equals to the sum of phase A positive sequence component and phase A negative sequence component and phase A zero sequence component, right? Exactly same thing, phase B equals to the phase B positive sequence component, who is equals to A squared times VA plus. plus phase B negative sequence components, who is equal to A times VA minus. And then plus the phase B zero sequence, which is equal to the phase A zero sequence, right? And so on and so forth for the phase C. So for each one of these three, you always have positive, negative, and zero sequence component. Okay. So this is the unbalanced total voltage. And obviously this column is what? Positive sequence, right? Positive sequence for phase A, B, and C. These three are what? Negative sequence components for phase A, B, and C. These are zero sequence for phase A, B, and C. Right? So writing a matrix A with these entries, we are able to find what? We are able to find the total unbalanced three-phase voltages based on the given, what is it called? What is it? What is it called? Anyone remember? What is it? This is nothing but voltage, what? Symmetrical component, right? Voltage symmetrical component. That's right. Daniel is right. Daniel is right. Okay. So this once again, this is given symmetrical component. You're looking for the total three-phase unbalanced voltages. Right. This is one way. We have the other way around. Given the unbalanced total three-phase voltage, look for the system voltage symmetrical component. Okay. Obviously, as the inverse matrix of A. And if you're writing them into the equations, simultaneous equations, then phase A positive sequence, phase A negative sequence, and phase A zero sequence respectively equals to the three equations like these. In terms of phase A, B, and C, and balance the total voltage, as well as A. Okay. By the way, what is A? A is phasor with magnitude of 1, phase angle of 120 degrees. Right? In complex number rectangle form that equals -0.5 plus 0.866J, right? It's complex number. So whichever you feel comfortable with, right? Well, as we said, it's very easy to make mistake of missing this 1/3, the coefficient 1/3. Where does this 1/3 come from? Matrix A's inverse matrix is giving you this constant coefficient 1/3. Okay, that is how. This is how. All right. So any questions regarding these knowledge? Regarding these concepts? Well, here we have a question from Sawyer previous. Is homework 2 going to be extended? Is homework 2 going to be extended? What does this mean? First of all, let's go to the module 2. Homework 2 is due by today. And what does mean by extended? You're asking for extension to the end of today, or I did that kind of extension before, but what is this specifically? Speak, come on, you guys have voice. I have ears. Those pairs functioning perfectly. Yeah.
Like Thursday, I guess.
Thursday. No. The end of today gonna be the end of today gonna be the best deal, but best offer. Not gonna be the best offer. Deal?
I mean, one of the per unit questions on that homework though,
Oh,
and we never even had an example.
oh, you got me. Okay, you got me. Thursday, what time?
Anytime you want.
All right. Let me extend to Thursday. Thursday. Why it has to be why Thursday, not Wednesday? Well, Thursday. You got me. You got me. You deserve it. Thursday, okay?
Thank you.
Yeah, sure. And also to the rest of you guys, as long as you guys can got me, okay, kind of got me, you're gonna deserve some good deal. All right? You have my word. Okay. Sawyer got a good point. Okay. And I'm not providing enough examples. That's why you deserve to be extended Thursday. 4 p.m. I don't want to change the time. Thursday, October 1st. All right, extended. All right. Any other questions? This is the homework 2. Okay. This homework 2. Okay. All right. If this is fine, then let's continue here. Last year in same class, I received a very good question. And students asking, you said this is the voltage symmetrical component, right? However, in this free system, what do you mean by voltage? Do you mean phase voltage or line voltage? That's a very, very good question, obviously. We need to emphasize, okay? Here, the voltage symmetrical component is and must be, okay, because this is the definition. This is about a definition. There's no alternative way, okay? There's no second option, only one way, okay? This voltage symmetrical component, this voltage must be a voltage, must be phase voltage, okay? Must be phase voltage, okay? It cannot be line voltage. All right, remember this. This is a very good question. That's a very good question. Okay, very good question. Because the given might be like the line voltage. Okay, the given might be line voltage. That's possible. That's absolutely possible. Okay, and here what we really looking for is the phase voltage. We're really looking for is phase voltage. All right. And so this is, I think is fairly easy. However, copy the correct formula. Okay. And because in the quiz I noticed, I don't know how, but delta load, the line current delta load equals what? The phase current delta load times square root of 3. I don't know where you guys got such answer, but so many of you make this exactly same mistake and making me thinking, well, maybe online solutions are telling you this. No, okay. You're missing a negative 3 degree. On your quiz, I'm writing the formula is not complete, is not completed. Okay, it's not completed. For delta load, your line current equals to the phase current times square root of 3 with negative 30 degree. Okay. And actually, I also double check my notes and the recorded lecture video and make sure I didn't make a mistake like this there. Okay. Negative 30 degree. Okay. Also here, going back to here, make sure you're copying the correct formula as well. Okay. Any questions? All right. If these are fine, then apply them onto some examples, and this should be very easy. Yeah, very straightforward. A three-phase unbalanced currents given as find a current symmetrical component. I don't think I need to provide any further help. Just to give you guys 5 minutes. It's kind of exercise for you to do the phasor calculation or stuff like that. So just to go ahead, find the current symmetrical component. But be very careful on those labels. Okay. What is the correct subscript and what is the correct proper superscript? Okay. Be very careful on those things. Okay. And then just go ahead. Just go ahead. Yeah. 5 minutes. All right, I think some of you have already done with this. So I step by step presenting the solution here. Okay. So first of all, the current symmetrical components meaning what? Okay, you need to understand the meaning. Phase A current for positive, negative, and zero sequence. Right? First of all, you need to understand who are they. Okay, you need to understand who are they, and then go back to your formula sheet. Right? And then what you find is actually this, right? Right. These are the formula we are applying. The rest of works are pretty much just to type them into the calculator, right? Calculator, right? And then the result should be like this. Okay. So take a look to see any questions. Are they same as yours, Kevin?
Yeah, that's what I have.
All right, good. I figure you're trying to type in your answers. Yeah.
Is A just 1.6?
No. A is here. A is a phaser. Okay, use phaser here. Phaser with magnitude of 1, phase angle of 120 degree. And if you prefer the rectangle format, is real number of 90.5, imaginary number of 0.866. Right?
Okay.
Yep. Yeah, make sure your calculator is friendly to you. Okay, I think that's very critical. That's very critical in the exam. Make sure it has full power. Make sure that the output, the results are in nice numbers. I in the quiz, I received an answer like this. I don't know how that happened. It's kind of like this. J times 2. I received a complex number result like that. I was like, well, your calculator is not very friendly. Make sure you're able to come up with a nice number. Okay, this is supposed to be whatever a real number, right? A real number plus a real number times j. But this result is not necessarily wrong. You're not losing any point necessarily. However, it's obviously takes some more time for no reason. That's right. So make sure your calculator works fine for you. Okay. Anyways, any questions regarding these results? I think it's really very really straightforward. Well, next let's do another small example. Try to plot them. Plot these three phasors. These are obviously three phasors into a phasor diagram. Phasor diagram. Let's do one of them. Let's do one of them. Okay, let's do one of them. Let's learn how to do this. When you try to plot more than one phasor into one same graph, phasor diagram graph, what you want to do is set up a what? Reference, right? Doesn't make sense. Obviously, you want to set up a reference. Without this reference, how could you come up with the angles? one reference horizontal axis might not be enough. Okay, so my suggestion is have at least two. The second one is obviously reasonable. This is what, 90 degree, right? This is the 180 degree. Then what is this? 27, right? 270, right? So you have this reference established, at least. I mean, I saw some students also give a middle line, a diagonal middle line, and anti-diagonal. That can also be helpful, but remember, don't mess up with the phasors you're gonna plot. Okay, and then we start to plot the phasor. How to plot the phasor? Phasor is a vector, right, in the space, meaning certain length representing the magnitude and certain angle degree with respect to the zero here representing the phase angle. Does it make sense? Now, therefore, how to plot the first one, 0.45. 0.45 magnitude with angle of 96.45 degree. How to plot this? And listen very carefully. Listen very carefully. You're not plotting like seeing first and then plot the first one. Okay, no, you're not doing that. You're not doing that. That's gonna likely to mess your graph up. The best way to do it is find the longest one to begin with. Does it make sense? Find the longest one, the biggest, the vector with the biggest magnitude. All right, because that's going to set up the capacity of your, or say the dimension of your entire graph. Okay, so begin with the biggest magnitude one. Here is obviously what? This guy, the second one, right? So it's close to 1, but it's okay. 0.94. How long it is, well, it doesn't matter. It's up to you. What matters is compared to the rest of the two, they must be in scale. Did I make myself clear? Okay. 0.94, 0.6, and 0.45. They relatively have a kind of comparison in terms of the length, as well as the phase angle. Right? Phase angle is easier since you have a reference here established. However, the length is all up to you. This is another reason why we begin with the longest one. So 0.94 with angle of basically 0. Okay. You set up a decent length. Okay. Don't make it too short. Don't make it too long either, right? Decent length. And being clear that the rest of two are going to be both shorter than this guy, right? Give a arrow here. It's not exactly 0, so I gave a very tiny off here. So, and then what we need to do is just label this guy as IA plus. Next, it doesn't matter actually the first, third one. Maybe the second one. Maybe the second one. Second one is about the John. Can you mute for a second? All right, thanks. It's a blah, 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 something like this. Okay. All right, let's plot the first one here with magnitude of 0.45. Magnitude of 0.45 means what? Half length, right? Half length, basically half length, right? Approximately half length, right? You don't have to be 100% accurate. This is the hand sketching, so there's no way to be that accurate. However, it must be in scale, as I said. 0.45 compared to the 0.94 is about half. Okay. Half is about what? This length, right? This basically this length with angle what? A little bit more than 90 degree. Okay. So the result is like this. Does it make some sense? This is IA0. Half length about this, okay, that's fair. That's fair enough. The third one is what? Third one is about 2/3 of the length of the second longest one. 2/3 of length. 2/3 of length is about here, right? About this long. With angle of 22, with angle of 22. 22 is where? 22 is about here. 22 is about here. And the is reached to this far. Label as IA minus. Does it make sense? How we come up with this graph? This also matter for how for future how I gonna grade you, right? I mean, if you give me like IA0 like this, well, it's obviously fair. Okay. So you're definitely gonna lose point. In terms of face angle, it's okay like this, close to 90 degree or even along the 90 degree. It's not very big deal. However, if you IA0, you're here, IA0, then the angle does not make any sense. It's even less than, way less than 90 degree. That couldn't be right. That couldn't be right. Right. So this is the phasor diagram. A phasor diagram. Is that also very informative? Any questions? Not difficult. Just be careful enough, and then you should be fine. All right. If this is fine, then give you guys 2 minutes to sketch the three-phase unbalanced total voltage, these three, into another phasor diagram. Give you guys 2 minutes. Go ahead. Oh, yeah. Receive a very good question and very good correction. I'm sorry. This is obviously not right. Folks, listen up. And you point it out. Okay. IA plus is not right? It's supposed to be here. Nearer. With respect to the zero reference, this is IA plus. Because of the negative sign here. Good, good. If you kind of figure that out, and then bring up. Okay, bring up. Thank you. And this appreciation credit is given to Anil. Well, so our reference is 0 degree. Of course, I labeled it as 0 degree. It is 0 degree. Horizontal line towards right is 0 degree. Yes, you're setting up a 0 degree. Without this setup reference, you can't determine the rest of the angles. All right, let's see what is the three-phase unbalanced total current, and then Obviously, once again, I'm beginning with the longest one, 1.6, 1.6 with 25 degree. 25 degree is about here. Is about here. And it is the longest one, so they give
Can you move the paper up?
Okay, here we go. Here we go. This is the IA. So 0.6 is length of 0.6. Next, 180 degrees. The angle is very easy, just here. Now the length is about what? Is 5/8 of the length. 5/8 is like what? 5/8 is a little bit more than half. A little bit more than half, right? This is half. So a little bit more than half is going to be here, right? I'm just up here. This is IB. Does that make sense? A little bit more than half. Third one is 0.9. 0.9 angle of 132 degree. 132 degree, be very, very careful. Be very, very careful. This is 90 degree, we know that. If you have a middle line here, a middle line now becomes significant. Okay, becomes very significant. So middle line here, what is the angle here? Anyone knows? What is the angle here? Middle line here. (135), very good. You see, that's why I'm saying the middle line here now becomes very significant because we are about to plotting a 132. Right? The 132.9 is actually basically about the half length of this guy, right? Half length of A. That's easier. However, 132 just a little bit to the right of this middle line, right? Which is IC. Does that make sense? A little bit right to this middle line here, right? Does that make sense? Any questions? And also be careful, okay? Compare IC and IB. You know that IC is supposed to be a little bit less than IB, and it should be the case. And from here, you can tell it's a little bit less than IB, or say very, very close. Okay. All right, no. And I'm seeing John is asking, would it be beneficial to have non-zero reference angle? No, I'm not seeing any benefit. Do you? And what is it? Okay. All right. So this is the example one. This is example one. Very straightforward, but just to make sure you're getting 15 out of 15 in the exam, right? That's your goal. That's your goal. That's your goal. All right. Before more examples, let's talk about power a little bit. Okay. I think it's very interesting to talk about power here. So to power. Here, let's just talk about the parent power. To power, how we integrate different sequence components into the picture, right, for the power. So first of all, unbalanced total power is equals to what? What do you guys think? Or let's begin with the balanced. We previously learned the three-phase balanced power, right? Equals to what? 3 V phase RMS times I phase RMS conjugate, right? Right. This is what we learned from the module 2. Very straightforward. Right. However, here I'm emphasizing this is balanced. Okay, it's balanced. What does it mean by balanced? Three-phase voltage and three-phase current have same magnitude, 120-degree phase shift. Right. So those are balanced. Line and loads must be equal. Yes, sure. Yeah, line impedance and loads, balanced load as well. Because that otherwise your current won't be balanced. Okay, a load must be balanced. A line must be balanced. Okay, otherwise your current won't be balanced. Okay, your voltage might be balanced, but your current obviously induced by the load, so it must be balanced too, right? However, balanced sequence are what? Positive sequence and a negative sequence. Does this make sense, folks? What I'm saying is positive sequence like this. Negative sequence like this. A, B, C, A, B, C, right? They're balanced. Same magnitude, same length, however, 120-degree phase shift, or just a different phase sequence. However, both are balanced, okay? So keep this in your mind. What does it mean by balance the system? Positive sequence itself and the negative sequence itself, they are individually balanced three-phase, right? Who is the unbalanced one? Who is the unbalanced one? Zero sequence. Because they have same magnitude, good. However, they don't have 120-degree phase shift, right? Their phase are same. So zero sequence, actually, this is what? Unbalanced, right? So if you mixing them up together, it becomes total unbalanced up here, which is going to be unbalanced as well. Does it make sense? So now how will you calculate the total unbalanced total three-phase power then? How? Any idea? Any idea? Well, just like we previously see from here, right? You see? So when you talk about a voltage, each phase total unbalanced voltage equals to what? Consists of three sequence components, right? Same idea. So this is total three-phase unbalanced power. What do we do? How about three-phase positive sequence? How about plus three-phase negative sequence? Plus three-phase zero sequence? How about this? You sum them up, right? It's just you have three sequence, then they're looking for the three-phase power for each one of them, and then summing them up, right? Does it make sense? And then we are glad to see that this guy is balanced. This guy is balanced. You know what to do. You know what to do to this. And then what do we do to the zero? What do we do to the zero? Zero is okay. Now it's remaining same equation. That's fine, right? So three-phase positive sequence. Current phase, positive sequence, conjugate, right? Does that make sense? Plus 3 phase, negative sequence, current phase, current negative sequence conjugate, plus 3 phase, 0 sequence, or phase sequence conjugate. Right? Does it make sense? And then what is phase voltage? What is phase current? Very easy. We choose what? Symmetrical component, right? 3VA plus IIA plus conjugate plus 3VA minus IA minus conjugate plus 3VA0 IA0 conjugate. Right. Here we go. Here we go. Right. This is the power. This is how we calculate the power. Does it make sense? How we deal with the power? So we basically sum up the 3 different sequence power. Right? This is the power. It's not something very difficult. I mean, as long as you know the symmetrical components for voltage and the current, then you are able to find the power. Right? Very straightforward. You need symmetrical voltage components, these guys, 3 guys. You need to know the symmetrical components for current, these 3 guys, right? And then that's it. Anyways, let me repeat this problem here. VA plus minus 0 is supposed to be 130 here, 0.8, 90, 30 here, and 0.6, 90 degree here. Try this one. And then this should be the answer over here. Let's see. Matrix or equations, it doesn't matter.
Yeah, I got the right answer now.
You got this answer?
I got the answer that you have written down.
Okay. Any other confirmation?
I got it too.
Okay, you got it too.
Looking at my first one, I mixed up my order after in the equation, which is why I had that different answer. So you must have done the same thing as me.
Well, actually, it's a similar mistake, but it's a different place. All right, folks. So let me summarize the problem of this. No, it matched with yours. Okay, thank you, Anil. But the thing is here. Okay, read carefully here. Read carefully here. The sequence here. Okay, the sequence here. It might be this way. That's possible. I mean, not only in the exam, but also in the textbook. So read the sequence here, okay? Read the order here. The first one is representing plus, minus 0 or 0 plus minus. There are 2 ways to write the superscript. Following this order, then we should end up with this result. Right. Thank you. Thank you. And well, I think in the exam I'm gonna give a little bit of credits to all of you guys to compensate your time wasted. Since I think I wrote the wrong order here, and sorry about that. And some free credits gonna be given in the exam. Okay.
Awesome.
And you'll probably be glad to see more mistakes from me, right? So, all right, good. If this is fine, then let's see the graph. The graph. Okay, let's see the graph. See the graph. Zero degree, 90 degree here. And then we begin with the longest one. We have two exactly same with angle of, well, what you see these two. What's the trick about the face angle here? They have a relationship, right? The face angle. Magnitude is exactly the same, and the face angle is about what? And therefore, this two vector becomes what? Can you tell?
Straight line?
What is it?
A straight line? Well, they add up to 180, so they're...
So they what? They're not straight line. I know what you mean.
They're pointing, they're pointing opposite directions.
No, they're not. Still not right. Still not right. I understand what you mean. However, you miss,
right?
You miss one. They are what? Symmetrical about the y-axis, about the 90 degree, right? Rather than along the same line. Not along the same straight line. I know what the NOA mean, but actually not, right? Let's just try to plot them. So first of all, the VA is like a 24 degree. A 24 degree is about here. With this is a VA. So here is 24.18 degree, right? This one, the degree here plus this guy equals to 180 degree. However, you need to count within this. So result is what? Result is this. Right? So exactly a mirror with respect to 90 degree, right? So this is VB. Does it make VC? I mean, right? Does it make sense? I mean, so here it has the same angle with here, right? So they're now along the same straight line. Okay, so there's a mirror, symmetrical about the 90 degree. So this is a VA and the VC. The VB has 1/4 of the length and the 90 degrees, so it's a quarter length. Okay, it's about here, which is VB. Right. So this is the VABC. No need to be 100% accurate. We actually we couldn't. However, just be fair. Yeah, just be fair. Okay? Just be fair. Any questions? Any concerns here?
I have a question.
Yep.
What would the matrix look like for those system equations?
Matrix. One more time. These matrix these matrix. There's nothing wrong with this matrix. You mean this matrix, right?
Yeah, that one works out, but you're... Oh, okay, they're set up just different.
The setup.
The zero sequence always gets put on that side. Okay, that makes more sense. All right, thank you.
Sure. I mean, once again, yeah, we need to be careful. This one in the exam. but not exact. I mean, the textbook and other literatures, it might be 0 plus minus. That's absolutely possible. I think if you got another matrix from somewhere else, like a Sawyer did, you probably end up with the different version of matrix. Okay, that's why. But once again, be careful this order. Okay, this order absolutely matters here. The plus minus 0 or 0 plus minus. Okay, it's telling you which is which. Right? So this is the matrix. Any other questions today?
So all of those must be phase voltage for the calculation. For current,
Correct.
is it
Phase current as well.
it's still phase current? Okay.
Yes. So it's kind of idea is kind of the source as voltage, right? Source of voltage or current is introduced. Therefore, its current is a phase current as well.
But
And
since the system isn't balanced, are we allowed to use? We can't, like, if we're given, let's say, instead of phase current, we're given line current. Because the system's not balanced, we can't just convert it to phase current, can we?
For each individual sequence, you can, right?
We can't, right?
We can for individual sequence, right?
Okay.
That doesn't make sense to you? Because the positive sequence and negative sequence individually, they are balanced, right? Any further questions? All right, that's it. And thank you for attending today's lecture. And talk to you guys on Wednesday. Bye now.